The autumn of 1984. A suburban kitchen, its wood veneer cabinets and avocado green countertops, a testament to the design ethos of the prior decade. On the table sat a box, large and heavy, containing what the packaging promised was the future of food preparation, an Amana Radarange RR1000. For the family gathered around, and especially for the 10-year-old child watching with rapt attention, this beige 65-pound appliance was not a mere oven. It was a portal to the world of tomorrow, a world of instant gratification promised by science fiction. The ceremonial first meal was chosen for its futuristic appeal, a personal frozen pizza. The directions printed on the back of the cardboard box seemed impossibly simple. 4 minutes on high, the small disc-like pizza, frozen solid, was placed on the glass turntable. The door was closed with a heavy, satisfying clunk, the digital timer set, and the button pressed. A low, unfamiliar hum filled the room, the sound of a 1.2 kilowatt magnetron beginning its work. It was the sound of progress. 4 minutes later, a series of electronic beeps signaled completion. The door swung open to reveal not a culinary triumph, but a thermal catastrophe. The outer crust, pale and doughy, had attained the simultaneous qualities of being both tragically soggy and impenetrably tough. Islands of shredded mozzarella remained stubbornly solid and cold, sitting directly adjacent to pockets of tomato sauce that had been superheated to a molten volcanic state. The first bite confirmed the full extent of the failure, a perimeter of icy, uncooked dough giving way instantly to a core of mouth-searing lava. It was a culinary paradox, a single object existing at multiple, incompatible temperatures. This moment of profound disappointment, repeated in millions of kitchens across America, was more than just a failed dinner. It was a tangible demonstration of the vast gulf between a technology's promise and the complex physics of its execution. The story of how convenience food would ultimately be mastered begins not with the appliance on the kitchen counter, but with the hidden, counterintuitive properties of water molecules under high-frequency electromagnetic radiation, and a problem that food scientists would come to call runaway heating. The thermal catastrophe witnessed in millions of American kitchens was not a failure of the microwave oven, but a symptom of a much deeper engineering dilemma. This was the frozen pizza paradox, a fundamental challenge that confronted food science in the late 1970s and early 1980s. The industry had sold the public on a vision of push-button convenience, but in doing so had promised to resolve a set of physical contradictions that bordered on the impossible. The task was to create a single, integrated product that had to survive the cryogenic cellular disruption of deep freezing at temperatures of -10 degrees Fahrenheit or -23 Celsius, and then, in a matter of minutes, achieve a state of differentiated culinary perfection within the chaotic, high-energy environment of an oven. The paradox was rooted in the pizza's construction. It was not a single, homogeneous object, but a laminated composite of materials with oppositional thermodynamic properties. At the base was the crust, a par-baked, low-moisture matrix of starch and gluten. For the crust to succeed, to become crisp, brown, and firm, it needed to achieve surface temperatures exceeding 350 degrees Fahrenheit or 177 degrees Celsius, driving off its remaining moisture and allowing the Maillard reaction to occur. But directly on top of this foundation lay its enemy, the sauce. The sauce was an aqueous suspension of tomato solids, typically comprising 85 to 90% water. When heated, this water turned to steam. Trapped beneath layers of cheese and toppings, that steam had only two directions to travel: up, into the insulating fat layer of the cheese, or down, directly into the porous structure of the crust. This downward migration of superheated water vapor was a direct thermodynamic assault on the crust integrity, transforming the carefully engineered bread base into a casualty of steam infusion, the source of the characteristic sogginess. Layered atop this central conflict were the final complicating variables. The cheese, a high-fat, moderate-moisture amalgam of milk solids and oil, was intended to melt at approximately 150 degrees Fahrenheit or 65 Celsius and stretch. But its high-fat content also meant it acted as an insulator, slowing heat transfer to the toppings above while deflecting heat back into the sauce below. Toppings themselves presented a chaotic range of properties. A slice of pepperoni with its low moisture and high fat content would crisp and render. A piece of green bell pepper containing over 92% water would dump its entire cellular moisture content onto the battlefield as it cooked, exacerbating the sog factor. The frozen pizza was therefore not one engineering problem, it was a half dozen, all existing in a 6-inch wide disc, all demanding contradictory outcomes at the exact same moment. It was a problem that could not be solved by a better oven. It had to be solved at the molecular level before the pizza ever reached the box. The central conflict between a wet sauce and a dry crust, however, was not an artifact of the microwave age. The story of this battle begins nearly 3 decades earlier, in the post-war optimism of the 1950s, a time when the home freezer was becoming a symbol of American abundance and convenience. Pioneers like the Celentano brothers of Verona, New Jersey, who began marketing one of the first commercially successful frozen pizzas in 1957, and Rose and Jim Totino of Minneapolis, who scaled their local operation into a national brand in the early 1960s, were the first to face this challenge at an industrial scale. Their products were engineered not for the high-frequency energy of a magnetron, but for the slow, radiant heat of the conventional home oven. Yet even in this simpler thermal environment, these early manufacturers confronted the same fundamental enemy that would later plague the radar range, the inexorable physics of moisture migration. The problem was not one of cooking, but of cryo-storage. A frozen pizza could spend weeks or even months in a grocer's freezer case, held at temperatures of 0 degrees Fahrenheit or minus 18 Celsius. During this time, the product was engaged in a slow, silent internal war. The sauce, with its high water activity, a measure of unbound water available to migrate, sat directly atop the par-baked crust, a porous starch matrix with a profoundly lower water activity. The laws of thermodynamics dictated the outcome. Driven by the universal tendency toward equilibrium, individual water molecules would gradually unbind from the tomato solids in the sauce and travel downward, seeping into the cellular structure of the crust. During the freezing and subsequent storage period, these migrating water molecules would coalesce into large destructive ice crystals. These crystalline spears would physically rupture the delicate, baked-in structure of the crust's gluten network. When the consumer finally baked the pizza weeks later, those ice crystals would melt, releasing their trapped liquid and leaving behind a texture that failed on every level. The promise of a crisp, satisfying crust was betrayed, replaced by a gummy, waterlogged foundation. This was the original, core challenge of the frozen pizza, a problem of chemistry and time, long before it became a problem of physics and heat. The solution to the problem of moisture migration, a challenge that had defined the first generation of frozen pizza, would emerge not from a single breakthrough, but from a fundamental shift in perspective. Food scientists in the research and development labs of companies like Totino's and Geno's realized they could not win a direct war against the laws of thermodynamics. The answer was not to defeat moisture migration, but to contain it. The realization was that the crust and sauce could no longer be treated as simple layers of a recipe. They had to be re-engineered as two components of an integrated system, separated by a deliberate engineered defense. This defense would come to be known as the moisture barrier. The first front of this new strategy was the crust itself. The original purpose of par baking had been simple pre-cooking. Now it was repurposed into a precise industrial process designed to create a physical shield. The crust was subjected to a short, high-temperature blast bake, often lasting less than 90 seconds at over 500 degrees Fahrenheit, or 260 Celsius. This intense heat did more than just cook the dough, it instantly gelatinized the starches on the crust's top surface, causing them to swell and form a smooth, less porous film. This process, combined with the initial denaturation of proteins, effectively seared the top of the crust, creating a laminated skin that was physically less permeable to migrating water molecules. It was in effect culinary armor plating. The second front was a chemical assault on the sauce's core problem, its high water activity. Scientists began reformulating tomato sauces with a new class of ingredients known as hydrocolloids and modified food starches. These substances, long-chain polysaccharides like xanthan gum, guar gum, and specially processed cornstarch, acted as molecular cages for water. When added to the sauce, even in small concentrations of less than 1%, Their polymer chains would uncoil and create a complex matrix that trapped and bound previously free water molecules. This did not reduce the amount of water in the source, but it dramatically lowered its water activity, sometimes from a level of 0.97 down to 0.94. This seemingly small numerical shift represented a profound change in chemical potential, vastly reducing the thermodynamic pressure driving water into the crust. Together, these two innovations, the physically sealed crust and the chemically bound source, formed the moisture barrier system. This system represented the first decisive victory in the war against the waterlogged crust. It solved the critical problem of cryostorage, allowing a pizza to sit frozen for months without its foundation being compromised by the formation of destructive ice crystals. For the first time, a frozen pizza could reliably emerge from a conventional oven with a crisp bottom. The paradox of the cold storage problem had been solved, but this victory only set the stage for a far more chaotic and energetic conflict, the battle that would have to be waged inside the high-frequency radiation field of the microwave oven. The moisture barrier system was a brilliant strategic defense, a culinary Maginot Line that held back the slow, persistent siege of moisture migration during storage. It solved the problem of a par-baked crust absorbing water from its source over a period of months. But this victory against a chemical foe, the battle against water activity, only served to reveal a far more violent and immediate enemy. This was a war of physics, waged not over months, but in the moments of freezing itself, at a microscopic scale. The engineers had discovered that what separated a crisp pizza from a soggy failure was not just the presence of water, but the very architecture of its frozen state. The core of the problem lay in the standard freezing process of the 1960s and 70s. In a typical industrial freezer, a pizza would be brought down to a holding temperature of degrees Fahrenheit or -18°C over a period of several hours. This was a slow, gradual transformation. Inside the cellular structure of high-moisture toppings like bell peppers, onions, or mushrooms, the water did not freeze instantly and uniformly. Instead, as the temperature slowly dropped below 32 degrees Fahrenheit, or 0°C, small seed crystals would begin to form in the extracellular fluid. These crystals then grew according to the laws of thermodynamics, drawing unbound water molecules from the surrounding cells in a process known as accretion. Slow freezing provided the one thing this process required: time. Over hours, these crystals grew into large, jagged dendritic structures, reaching sizes of 200 to 500 micrometers, large enough to be seen with a basic microscope. These were not benign structures. They were crystalline spears, microscopic daggers that physically punctured and tore through the delicate cellular walls of the vegetables, and even the protein and fat matrix of the cheese. What was once the organized, turgid structure of a plant cell, holding its water content neatly inside, was left as a landscape of cellular wreckage. The structural integrity of the toppings was systematically destroyed before the pizza was ever placed in its box. The product was, in effect, catastrophically damaged at a microscopic level, its future failure locked in by the physics of its own preservation. The consequences of this microscopic violence became evident the moment the pizza was cooked. As the temperature inside the oven rose, the massive ice crystals melted, but the water they released could not be reabsorbed by the now ruptured cells. It was liberated as a sudden, uncontrolled deluge of free-flowing liquid. This is what created the signature failure of early frozen pizza. The pools of water that formed around toppings, turning what should have been crisp roasted vegetables into a watery stewed mess. This liquid then cascaded downward, overflowing the sauce layer and overwhelming the par-baked crust defenses. The crust, which had been engineered to withstand a slow chemical siege, was no match for a sudden physical flood. It became saturated, turning into a steaming gummy paste. The primary enemy had been identified. It wasn't merely water, it was the ice. The solution to the microscopic violence of ice crystal formation would not come from the pizza industry's own research labs. It would be adopted from the work of a man who had made his breakthrough observation decades earlier, surrounded by the sub-zero wind of the Arctic. The answer was a radical change in philosophy, a complete inversion of the freezing process. The industry had to learn the lessons of Clarence Birdseye, the father of modern frozen food, who had observed in the 1920s that fish caught by Inuit fishermen in Labrador at temperatures of -40 degrees Fahrenheit or -40°C and frozen almost instantly by the Arctic wind, retained a perfect fresh texture when thawed and cooked. The insight was fundamental. The destructive power of ice was not a constant. It was a function of time. This observation represented a new doctrine in the war against cellular destruction. Slow freezing, conducted over several hours, gave water molecules the time they needed to migrate out of the food's cells and accrete into the large spear-like extracellular crystals, the 200 to 500 micrometer daggers that shredded the cellular architecture of toppings and cheese. Fast freezing, Birdseye proved, was a war of speed. By dropping the temperature with overwhelming velocity, water was given no time to migrate. It was locked in place and forced to freeze inside the cells, a process called intracellular vitrification. This created countless tiny ice crystals, typically smaller than 50 micrometers. These crystals were too small to physically rupture the cell walls. The food's microscopic structure, its very texture, was preserved. Embracing this doctrine meant re-equipping the entire production line. The pizza industry entered an arms race of thermal transfer, investing in capital-intensive technologies designed for one purpose: to remove heat as fast as physically possible. The first weapon in this new arsenal was the blast freezer. Here, assembled pizzas were placed on a conveyor belt that moved through a long insulated tunnel. Inside, massive fans blasted them with air chilled to minus 40 degrees Fahrenheit, moving at speeds of up to 5 meters per second. The combination of extreme cold and high-velocity air dramatically accelerated the rate of heat exchange, dropping the core temperature of the pizza to freezing in a matter of 20 to 30 minutes, not hours. But the ultimate expression of this war on time was the cryogenic tunnel. This technology abandoned chilled air entirely in favor of direct contact with liquefied gases. Pizzas moving down the conveyor would be sprayed with or pass through a fog of liquid nitrogen at a temperature of minus 320 degrees Fahrenheit or minus 196 Celsius. The thermal shock was instantaneous and absolute. The exterior of the pizza was frozen solid in seconds. The entire product could be brought to a stable frozen temperature of 0 degrees Fahrenheit in as little as 3 to 10 minutes. The battle was won not by finesse, but by overwhelming thermodynamic force. By freezing the pizza so fast that physics itself prevented large, destructive ice crystals from forming, engineers had finally created a product that could survive its own preservation. The structural integrity of the toppings was no longer a casualty of the freezer. The late 1970s. In the corporate boardrooms of Minneapolis, Chicago, and White Plains, New York, executives at Pillsbury, Kraft, and General Foods studied a set of charts with a mixture of avarice and alarm. The data depicted a market disruption of unprecedented velocity. The home microwave oven, an appliance that had been a $500 niche luxury only a decade prior, was now the fastest-growing major appliance in American history. By 1978, annual sales had surged past 2.2 million units, and forecasts projected that nearly 25% of all US households would own a microwave by the early 1980s. The numbers revealed a tectonic shift in consumer behavior and a potential market for microwave-specific convenience foods that analysts valued in the billions. The food industry saw an opportunity to mount a decisive offensive into the American kitchen. Their initial strategy was one of pure marketing, a belief that the battle could be won with new packaging and revised instructions. The industry's vast inventory of frozen products, pizzas, pot pies, and dinner entrees had been painstakingly engineered over 2 decades to perform in the slow, radiant heat of a conventional oven. Executives, viewing the microwave as simply a faster oven, directed their teams to repackage these existing products. The assumption was that a different set of cooking times printed on a new box was all that was required to conquer this new technological territory. It was a catastrophic misreading of the physics involved. The results were not just failures, they were a corporate embarrassment played out in millions of homes. The oven-centric pizzas, which had been perfected to survive cryogenic storage and emerge crisp from a 400-degree oven, became the poster children for this strategic blunder. Consumers followed the new instructions only to be met with the same thermal chaos experienced by first-time users: gummy, steaming crusts, frozen toppings, and cores of superheated sauce. The avalanche of consumer complaints, product returns, and damage to brand reputation was overwhelming. Within months, The executive suites of the food giants were forced to confront an uncomfortable truth. This was not a marketing problem. It was a fundamental crisis of engineering. They had mastered the slow, chemical war of the freezer, only to be completely routed in the high-speed radiological battlefield of the microwave. An urgent directive, backed by immense research and development budgets, was issued down the chain of command to the food scientists and engineers. Their mission was now an existential one: solve the microwave problem. To solve the microwave crisis, the food industry's engineers had to abandon the familiar century-old language of conventional heat transfer, conduction, convection, and radiation. They were forced to descend into the new and counterintuitive realm of high-frequency physics. The problem, they discovered, was not that the microwave oven was a bad oven. It was that it wasn't an oven at all. It was a targeted energy weapon, and its target specificity was the precise cause of the thermal catastrophe unfolding in kitchens across America. The source of this chaos was the magnetron, a vacuum tube generating high-power microwaves at a frequency of 2.45 gigahertz. Unlike the radiant heat of an oven element, which slowly heats the surface of food, this radiation penetrated the food to a depth of approximately 1 to 2 centimeters. Its heating mechanism was not a brute force application of temperature, but a process known as dielectric heating. This process did not affect all molecules equally. Instead, it selectively and violently agitated one specific type of molecule, a polar molecule. The quintessential polar molecule in all food is water. A water molecule, H2O, is electrically asymmetrical. Its oxygen end carries a slight negative charge, while its hydrogen end carries a slight positive charge, creating a molecular scale magnet with a north and south pole. The microwave's oscillating electric field, reversing its polarity 2.45 billion times per second, acted as an irresistible torment to these molecules. Each water molecule was savagely twisted back and forth, attempting to align itself with the rapidly flipping field. This relentless, high-speed oscillation generated intense intermolecular friction. This friction was the heat. Herein lay the fundamental reason for the frozen pizza's failure. Its components did not face this radiological assault as equals. The tomato sauce, containing 85 to 90% water, was a perfect, efficient receptor for microwave energy. Its vast population of polar water molecules began to vibrate violently, leading to a runaway heating effect that could bring the sauce to a volcanic, superheated state in under 2 minutes. Meanwhile, the crust, a matrix of starch and proteins with very low moisture, and the cheese and pepperoni, composed largely of fats and oils, were made of non-polar molecules. The microwave radiation passed through them with almost no effect. They were, in a very real sense, invisible to the energy being deployed. The result was the signature thermal paradox. The sauce boiled, but the crust it sat on remained cold, tough, and pale. The only heat imparted to the crust and cheese came from secondary conduction, from the molten sauce itself. This slow, inefficient transfer of heat was enough to turn the cheese into a lukewarm, rubbery mat and steam the crust into a gummy paste, but it could never reach the 350-degree Fahrenheit temperatures required for a crisp, browned texture. The food scientists now understood the terrible clarity of their problem. The microwave oven had divided their carefully engineered product against itself, turning its high-moisture component into an agent of destruction against its dry, fatty structure. It was a war of physics, and they had armed only one side. While the engineering core of the major food conglomerates descended into the radiological chaos of the microwave, a different conclusion was being reached in the research laboratories of their competitors, most notably at Kraft. The directive to solve the microwave problem was interpreted by some not as a mandate, but as a strategic error. For this contingent of food scientists, the battle was not worth fighting. They saw that a product optimized for the violent, uneven heating of a magnetron would always be a compromise, a pale imitation of the real thing. Their analysis was that victory lay not in accommodating the microwave, but in making the conventional oven an indispensable destination for the perfect frozen pizza. This decision represented a fundamental shift in the definition of the problem. The goal was no longer to create a pizza that could merely survive a microwave. The new objective was to create a frozen pizza that, when baked in a standard home oven, was texturally and gastronomically indistinguishable from fresh, hand-tossed pizzeria dough. This meant abandoning the decades-old paradigm of the par-baked crust entirely. A reheated crust, no matter how well formulated, would always carry the textural signature of being a leftover. To achieve true authenticity, the dough had to be frozen raw, and it had to perform its final dramatic rise for the first and only time inside the consumer's oven. The central challenge was leavening. Creating a dough that could lie dormant for months at -10 degrees Fahrenheit and then rise perfectly upon baking was a monumental feat of chemical and biological engineering. The first part of the solution was purely chemical, a sophisticated dual-stage leavening system embedded directly into the dough matrix. The formulation included sodium bicarbonate, the common alkaline base, but paired it with two distinct acids. The first acid, a fast-acting monocalcium phosphate, would react with the bicarbonate the moment water was added on the factory assembly line, creating an initial aeration in the dough before it was frozen. The second, a heat-triggered acid like sodium acid pyrophosphate, was designed to remain completely inert during mixing, freezing, and storage. It would only begin its reaction when the pizza's internal temperature passed 140 degrees Fahrenheit, or 60 Celsius, inside the consumer's oven, releasing a powerful secondary surge of carbon dioxide gas that drove the all-important oven spring. But chemical leaveners alone, while providing lift, could not replicate the complex fermented flavour and delicate crumb structure of a true yeast dough. This required a biological solution, and its implementation was a masterstroke of process engineering. The yeast, a specific cryo-resistant strain of Saccharomyces cerevisiae, could not be mixed directly into the dough. Its activity had to be perfectly controlled. The solution was to isolate it completely. In what would become a signature of this new category, the pizza was accompanied by a separate foil-lined packet. Inside was not just yeast, but a precisely formulated blend of yeast granules and sugar-based nutrients, kept perfectly dry and dormant in a nitrogen-flushed atmosphere. This packet was the biological key, held in stasis, waiting for its moment. The result was a symphony of leavening, conducted by the heat of the oven. The end user, following the instructions, would open this packet and sprinkle the yeast complex onto the pizza just before baking. As the oven warmed, the previously frozen dough would begin to thaw, rehydrating the yeast. This awakened the microorganisms, which immediately began metabolizing the sugars and releasing their own carbon dioxide, creating the authentic flavor compounds and fine bubbles characteristic of true bread. Then, just as the rising temperature would kill the yeast, the second stage chemical leavener would take over, providing the powerful final lift that inflated the crust to its full airy height. It was an unprecedented 1-2 punch of biology and chemistry. This was not a 4-minute meal. It was a deliberate, just 20-minute process that represented a calculated bet that a significant portion of the American public would willingly trade the promise of speed for the guarantee of quality. It was a declaration that the hearth of the conventional oven still held a power that the hum of the magnetron could never hope to match. Back in the microwave development labs of Pillsbury and other food giants, the war room atmosphere of early 1980 was giving way to a grim intellectual stalemate. The engineers had mapped the battlefield with terrible clarity. The enemy was not the oven, but fundamental physics. The weapon, the magnetron, was unchangeable, its 2.45 GHz frequency a fixed property of the appliance. The target, the frozen pizza, was an immutable composite of oppositional materials. Its watery source would always absorb microwave energy with violent efficiency, and its fatty, low-moisture crust would always remain stubbornly, transparently indifferent to it. Every attempt to reformulate the food itself, to make the crust more receptive or the sauce less so, was a strategic dead end, resulting in products that were texturally and gastronomically unacceptable. The problem, it seemed, was insoluble. A product designed with a dry base and a wet topping was fundamentally incompatible with the principles of dielectric heating. The breakthrough, as it often does, came not from a complex new formula, but from a radical reframing of the question. For months, the entire research effort had been defined by a single objective: how to make microwave energy cook the existing pizza correctly. But defeated by the physics of that interaction, a handful of engineers began to pose a different, almost heretical question. If you could not change the nature of the microwave energy, and you could not fundamentally change the composition of the pizza, what if you could introduce a third element? What if you could place something else in the oven, a tool that would intercept the microwave energy and use it to create an entirely different kind of heat? This question marked a pivotal shift in thinking, a moment of profound conceptual realignment. The old strategy was to fight a losing battle against the microwave's selective heating. The new strategy was to treat microwave energy not as a cooking method, but as a power source. The vision that emerged was elegantly simple. Instead of trying to get the microwave to cook the crust, what if you could put a tiny, disposable conventional oven inside the microwave? This oven would be a platform, a sleeve, or a disc, engineered specifically to get dangerously hot under microwave radiation, and then transfer that heat to the pizza crust through old-fashioned, reliable conduction. The same way a hot stone or a steel pan works. The microwaves wouldn't cook the crust. They would heat the thing that cooks the crust. This conceptual breakthrough immediately transformed the problem from one of food science into one of material science. The quest was no longer for the perfect dough, but for a new, smart material. This material, which would come to be known as a microwave susceptor, needed a specific and paradoxical set of properties. It had to be a lossy dielectric, meaning it was highly efficient at absorbing microwave energy and converting it into thermal energy. It needed to be capable of reaching temperatures in excess of 400 degrees Fahrenheit, or 204 Celsius, in under a minute. And it had to be formed into an ultra-thin, food-safe film that could be laminated onto cheap disposable paperboard. The target was no longer a recipe. It was a high-tech energy conversion device, disguised as a piece of cardboard. The engineers had redefined their mission. They were no longer trying to force an outcome against the laws of physics. They were now attempting to build a device that would expertly exploit those same laws to their own advantage. The war against the microwave was over. The race to harness it had just begun. The redefinition of the problem from food science to material science had created a new, and in some ways more profound, intellectual impasse. The research and development departments at Pillsbury, General Foods, and their competitors were staffed by chemists, biologists, and culinary experts, masters of hydrocolloids, cryo-resistant yeasts, and rheology. They were not, however, metallurgists or specialists in high-frequency physics. The problem of the susceptor had officially left the test kitchen and entered a domain for which the entire food industry had no map. Their internal expertise, which had brilliantly solved the challenges of freezing and storage, was now functionally obsolete. They knew what they needed, but had no idea how to create it. This forced the engineering teams to begin a process of discovery that led them far outside the familiar confines of their own industry. The search was a methodical exploration of any field that dealt with the manipulation of materials at a microscopic level, or the interaction of those materials with electromagnetic energy. This quest led them down parallel, and at first seemingly unrelated, paths into the high-technology sectors that had defined the post-war scientific boom. The worlds of electronics, advanced optics, and even defense contracting. The first trail led into the heart of the burgeoning semiconductor industry. In the 1970s and early 80s, companies like Intel and Texas Instruments had perfected the art of photolithography, a process of depositing microscopically thin, patterned layers of conductive and resistive materials onto silicon wafers. While the end goal was a microprocessor, the core competency was a technology known as thin film deposition. This was the precise science of laying down a film of a given material, often a metal, to a thickness measured in angstroms, or tenths of a nanometer. It was nanotechnology, decades before the term entered the popular lexicon. To the food scientists, this was a revelation. An entire industry was predicated on creating thin, electrically active layers on a substrate. The substrate was silicon, but the principle was what mattered. A second trail led to an even more unlikely source, the secretive world of military and aerospace engineering. Here, the goal was not computing, but controlling radiation for different purposes. This included the vacuum metallization of fighter jet canopies and astronauts' helmet visors with infinitesimally thin layers of gold to reflect solar radiation and radio frequency interference. It also included research into radar-absorbent materials, coatings designed to absorb specific microwave frequencies, converting them to heat and rendering an aircraft less visible. These industries had perfected techniques like vacuum sputtering, a process where ions were used to bombard a metallic target, dislodging individual atoms that then coated a substrate in a uniform, ultra-thin film. The stunning realization was that these disparate fields had all converged on the same fundamental technology. Whether for a computer chip, a telescope mirror, or a stealth aircraft, the core process was thin film metallization. The food engineers saw the path forward. They could license this technology. They could take a roll of cheap food-safe polyester film, the same clear plastic used in countless other packaging applications, and run it through a massive vacuum deposition machine. In this chamber, a small amount of aluminum would be vaporized, coating the plastic with a metallic layer just 100 to 500 angstroms thick. This film was the miracle they had been searching for. The aluminum layer was too thin and discontinuous to act like a sheet of foil, which would reflect microwaves and cause dangerous arcing. Instead, it existed as a vast field of microscopic, isolated metallic islands. When bombarded with 2.45 GHz radiation, these islands would furiously absorb the energy, acting like billions of tiny, inefficient resistors. The energy, unable to flow easily, was instantly converted into intense, searing heat. The food scientists had found their weapon. It was not a recipe or an ingredient. It was a high-tech manufacturing process, borrowed directly from the worlds of silicon chips and military hardware, that could turn a simple piece of plastic laminated cardboard into a frying pan. The genius of the new technology, the susceptor film, lay not in its composition but in its structure, a masterpiece of material science operating at a scale that defied intuition. To the consumer, it was a simple grey disc or a sleeve. To a physicist, it was a finely tuned energy conversion device. Its function was predicated on a single, counterintuitive principle. It was a layer of metal meticulously designed not to behave like metal. A solid sheet of aluminum foil, what physicists call a bulk metal, placed in a microwave oven, acts as a near-perfect mirror for 2.45 GHz radiation. The microwaves are reflected, creating destructive standing waves and powerful electrical potentials between the foil and the oven's metal walls, resulting in the dangerous phenomenon of arcing, a miniature lightning storm. The susceptor avoided this fate because the aluminum layer deposited onto the polyester film was not a solid sheet. It was a phantom, an illusion of a solid. The vacuum deposition process created a metallic layer of a precisely controlled thickness, typically between 100 and 500 angstroms. This is a scale that is difficult to comprehend. At 300 angstroms, the layer is over 1,000 times thinner than a single sheet of household kitchen foil. At this infinitesimal thickness, the aluminum did not form a continuous conductive plane. Instead, it formed a vast two-dimensional archipelago of microscopic metallic islands, separated by gaps mere atoms wide. It was a metal film that was purposefully, structurally discontinuous. This was the key to its function. When the 245 GHz radiation slammed into this landscape of isolated islands, it induced powerful electrical currents within each microscopic speck of metal. But because the islands were not connected, the current could not flow. It was like trying to drive a superhighway's worth of traffic down a disconnected series of dead-end streets. According to the first law of thermodynamics, this energy had to go somewhere. Trapped within the metallic islands with no conductive path to follow, the electrical energy was instantly and violently converted into thermal energy. The archipelago of islands became an archipelago of microscopic blast furnaces. The effect was transformative. In less than 60 seconds, the susceptor film could reach temperatures exceeding 450 degrees Fahrenheit or 232 Celsius. This intense heat was then transferred directly to the pizza's base via two primary mechanisms: conduction, where the crust was in direct physical contact with the searing hot surface, and thermal radiation, as the film blasted the bottom and sides of the crust with infrared energy. The microwaves were no longer cooking the crust. They were powering a disposable high-temperature skillet that was doing the cooking for them. The engineers had not just found a loophole in the laws of physics, they had weaponized it to create a perfectly crisp crust in 90 seconds. The discovery of thin film metallization was more than a case of technological borrowing. It represented a moment of profound intellectual convergence where the food industry, pushed to the brink of a physics problem it could not solve, stumbled into a parallel universe of engineering that had been grappling with the exact same fundamental principles for entirely different reasons. The engineers searching for a crisp crust had unknowingly walked into the domain of stealth warfare. The solution to the soggy pizza paradox had been developed in secret by designers whose goal was to make a multi-ton aircraft disappear from an enemy's radar screen. This was the stunning, counterintuitive truth. The technology that would perfect the microwave pizza was a direct civilian application of the physics governing radar absorbent materials, or RAM, the cornerstone of military stealth. A radar system works by sending out a powerful pulse of microwave radiation and detecting the energy that reflects back from an object. The central challenge of stealth technology, therefore, is to avoid this reflection. One of the principal methods for achieving this is to coat an aircraft in materials that are intentionally lossy, materials that are exceptionally efficient at absorbing the incoming radar energy and converting it into a different, non-detectable form, low-grade waste heat. The radar pulse hits the aircraft. Its energy is transformed into a slight increase in the temperature of the aircraft's skin, and almost nothing is reflected back to the receiver. The aircraft becomes a ghost on the screen. This Susceptor film was engineered to be a perfect, if miniature, expression of this same principle. It was a material specifically designed to be incredibly lossy at a frequency of 2.45 GHz. The goal was not to make the pizza invisible, but to weaponize the absorption process that stealth technology sought only to dissipate. While RAM converts radar energy into waste heat to achieve invisibility, the Susceptor converted microwave energy into useful heat to achieve crispness. The isolated aluminum islands performed the same function as the ferrite particles in a stealth coating. They intercepted electromagnetic radiation and, through engineered inefficiency, transformed it into thermal energy. The implications were as profound as they were ironic. The same fundamental law of physics, the controlled conversion of electromagnetic energy into heat, was simultaneously solving one of the Pentagon's most classified strategic challenges and one of Pillsbury's most frustrating consumer complaints. The quest for a crisp 90-second crust had led, through a chain of industrial and scientific logic, directly to the heart of the military-industrial complex. The physics used to make a bomber disappear was now being harnessed to make a pizza crust appear perfect. The moment of truth arrived on a winter afternoon in early 1982, inside a pristine test kitchen at the Pillsbury Research and Development Center in Minneapolis. An engineer, a veteran of the microwave crisis who had overseen hundreds of failed tests, took a standard-issue frozen pizza from a commercial freezer. It was identical in every way to the products that had failed so catastrophically in the marketplace. There was, however, one critical addition. He placed the frozen disc not on a glass plate, but onto a stiff grey circle of paperboard, the first production-grade prototype of the Susceptor disc. With a practiced motion, he slid the assembly into a conventional 700-watt consumer microwave oven and set the timer for 2 minutes. He pressed Start. The familiar low hum of the magnetron began. For the first 60 seconds, nothing looked different. The cheese began to soften. But then, an entirely new phenomenon occurred. A sound, faint at first, then unmistakable, began to emanate from the oven. It was a sound no one had ever heard from a pizza in a microwave before. It was the sound of frying. Through the radiation-shielded glass of the oven door, the engineer could see vapor, not rising from the top of the pizza, but escaping horizontally from the razor-thin gap between the crust's bottom edge and the grey disc. The superheated Susceptor film, now reaching temperatures in excess of 400 degrees Fahrenheit, or 204 Celsius, was furiously boiling away the minuscule amounts of moisture on the crust's surface. It was acting as a microscopic high-temperature griddle. When the timer beeped, the engineer opened the door to an unprecedented sight. The pizza looked, from the top, perfectly cooked. The cheese was melted and bubbling, the pepperoni was glistening. But the real test came when he slid a spatula beneath it. There was no gumminess, no sog. The crust lifted as a single rigid unit. He turned it over. The bottom, for the first time in the history of microwave pizzadom, was not pale and damp. It was golden brown, firm and dry to the touch, with a pattern of darker spots where contact with the hottest parts of the Susceptor had been most direct. He tapped it with the edge of the spatula. It produced a sharp, resonant thwack. This was the sound of victory. The experiment had confirmed the theory in spectacular fashion. The Susceptor disc had performed its function with devastating efficiency, cooking the crust from the bottom up with intense conductive heat. At the same time, the microwaves had passed through the now hot disc unimpeded, performing their parallel task of dielectrically heating the water-rich sauce and toppings from within. It was two distinct cooking methods, one ancient, one modern, working in perfect orchestrated synthesis. The paradox was solved. The war was won. The victory in the Minneapolis test kitchen was profound, but it was also singular. The perfect 90-second pizza crust proved a theory. But to move from a single prototype to the hundreds of millions of units required to stock every grocery store in America demanded a leap not merely in scale, but in industrial philosophy. Pillsbury, Kraft, and General Foods were masters of food science and mass production, but their expertise ended at the loading dock. They knew how to make dough, sauce, and cheese factories. They had absolutely no capability to build and operate the machinery that created the Scepter film. It was an entirely different technological universe. This was not a problem that could be solved with bigger mixers or faster conveyor belts. The manufacture of Scepter film was a process borrowed from the semiconductor and aerospace industries, and it required their tools. The core of the operation was the vacuum deposition chamber, an enormous, complex, and brutally expensive piece of capital equipment. These were multi-story, stainless steel behemoths, sometimes over 100 feet long, that required cleanroom environments and consumed megawatts of power. Inside, massive cryopumps would pull a vacuum harder than that of outer space, creating a void into which a precisely controlled amount of aluminum could be vaporized and deposited onto a rapidly moving roll of polyester film, laying down a metallic layer just a few hundred atoms thick. This was nanotechnology at an industrial scale. The food giants, faced with the prospect of building this capability in-house, quickly concluded it was an economic and technical impossibility. The capital investment would be astronomical, and the required expertise in plasma physics and high vacuum engineering was completely alien to their corporate DNA. This capability gap created a new, lucrative, and highly specialized industrial niche. It created a need for a new kind of supplier. A handful of companies, operating at the intersection of material science and high-volume manufacturing, recognized the opportunity. They saw a future where the humble frozen pizza box would contain a component born from the same technology that coated stealth fighter canopies. Firms like the James River Corporation, a Virginia-based paper company, and the Minnesota-based material science giant 3M invested hundreds of millions of dollars throughout the early 1980s to become the high-tech foundries of this new era. They built the massive vacuum chambers and perfected the process of producing metallized film by the square mile. A new B2B industry sprang up, dedicated to one single purpose: to supply the food industry with a magic film that could turn a simple piece of paperboard into a disposable high-performance frying pan. The food companies were no longer just making pizzas. They were now the final assemblers for a complex multi-layered technological product. The victory of the material scientists and the successful ramp-up of industrial production did not mark the end of the war for the microwavable pizza. It merely opened a new, and in many ways more vicious front. The battleground shifted from the laboratory and the factory floor to the corporate boardroom and the courtroom. The combatants were no longer engineers fighting the laws of physics, but lawyers fighting over intellectual property. The prize was not a crisp crust, but the exclusive legal right to produce one, a right valued in the billions. The Scepter was not merely a component, it was a revolutionary technology, and the corporate giants who had funded its development immediately moved to claim ownership. What followed was a strategic blitzkrieg on the United States Patent and Trademark Office. Beginning in the early 1980s, Pillsbury, General Foods, Kraft, and the material science firms like James River Corporation and 3M filed a torrent of patent applications. Each was an attempt to encircle and claim a piece of this new technological territory. The filings were a dense matrix of overlapping claims. Pillsbury sought patents for the food item and package combination, attempting to own the application of the technology. James River filed its own, including what would become the cornerstone US Patent 4006-41,005, covering the laminated microwave heating structure, aiming to own the device itself. This created a fundamental and legally ambiguous conflict. Did the invention belong to the company that first conceived of using a Scepter to crisp a crust, or to the company that had perfected the nanotechnological process to create the film that made it possible? It was a question with no clear answer, and the immense financial stakes ensured it would be settled not by engineers, but by litigation. The legal departments of these food conglomerates, once focused on trademarks and regulatory compliance, were transformed into frontline command centers in a high-stakes patent war. The resulting legal battles raged for years, consuming hundreds of millions of dollars in fees and settlements. Patent infringement lawsuits and countersuits became a standard cost of doing business in the new frozen food aisle. The fight was over who owned the rights to a physical process, the controlled conversion of microwave energy into conductive heat. It was a conflict born the moment that first prototype proved that a 90-second, perfectly crisp pizza was no longer a theoretical impossibility. The patent wars had begun. The patent wars of the early 1980s were fought over the future of a single iconic product, the 90-second microwave pizza. Yet while the legal departments of the food giants were locked in a multi-front conflict over the rights to a Susceptor disk, the technology's first decisive commercial application would emerge not from their heavily funded R&D divisions, but from a smaller, more agile competitor in Inglewood, Colorado. The first field application to achieve blockbuster success was not a pizza at all. It was a product launched in 1983 by a company named Chef America, Inc., a dough-enrobed, cheese and meat-filled turnover that would come to define an entire generation of after-school snacks, the Hot Pocket. The genius of the Hot Pocket was not in its recipe, but in its reconception of the Susceptor's purpose. The Pillsbury engineers had designed a disk to function as a flat, open-air griddle. Chef America's engineers integrated the Susceptor film into a folded paperboard sleeve. This seemingly simple change in geometry represented a fundamental leap in engineering effectiveness. The pizza disk had to contend with the chaotic thermodynamics of an open-faced product. The Hot Pocket sleeve, by contrast, created a closed, self-contained, high-temperature system. It was no longer just a hot plate. It was a disposable, single-use convection oven. When microwaved, the sleeve performed two functions simultaneously. The Susceptor film itself reached temperatures over 400 degrees Fahrenheit, browning and crisping the dough through direct conduction, just as the disk had. But the sleeve's folded structure also trapped that intensely radiated heat, creating a pocket of superheated air that enveloped the product. This allowed the exterior of the dough to be cooked by both conduction and radiation, achieving a consistent browned and crispy texture across its entire surface. Meanwhile, the microwaves passed through the sleeve to heat the high moisture filling from within. It was a perfect, elegant and self-contained execution of the dual heating principle. The results were transformative. The crisping sleeve, as it was iconically named, solved the microwave texture problem with a simplicity and efficiency that the more complex pizza application had yet to achieve in the marketplace. It was foolproof. For millions of American teenagers and time-pressed adults, it delivered on the original unfulfilled promise of the microwave oven, a hot, satisfying meal in 2 minutes that was not a thermal or textural catastrophe. The Hot Pocket became the Susceptor's first true killer app, a category-defining blockbuster that proved the immense commercial power of a technology born from the esoteric worlds of semiconductor physics and stealth warfare. The blockbuster success of the Hot Pocket's crisping sleeve represented more than a commercial victory for a single product. It was a moment of profound psychological recalibration for the American consumer. For nearly a decade, the word microwavable had been a functional synonym for compromise. It connoted a culinary surrender, an acceptance of sogginess and textural failure as the unavoidable price of speed. The limp pot pie, the steaming breaded patty, the thermally chaotic pizza, these were the known accepted casualties of the magnetron's radiological war. The crisping sleeve shattered this core assumption. For the first time, the word microwavable could mean something else entirely. It could mean hot and crispy. The psychological impact was immense. The technology had delivered on the original, long-betrayed promise of the Radirange, a perfect meal, in minutes, without compromise. The cognitive dissonance was resolved. A microwave did not have to mean a soggy dinner. This redefinition of a single word in the consumer lexicon was the market signal the entire food industry had been waiting for. Inside the research and development centres of Pillsbury, Stouffer's and Swanson, the success of the Susceptor sleeve was a decisive turning point. Product categories that had been written off as fundamentally incompatible with dielectric heating were suddenly viable. The engineering problem had been solved, and more importantly, the market had demonstrated its acceptance. The investment in vacuum deposition and the vicious patent wars had been validated. The dam had broken. The result was an industrial avalanche. A new generation of products once deemed impossible for the microwave began to appear on grocers' freezer shelves with unprecedented speed. There were microwavable French fries, a product whose entire existence depended on achieving a golden brown exterior previously exclusive to the deep fryer. There were pot pies from brands like Swanson, whose flaky, buttery crusts could now be achieved without a 45-minute bake. There were breaded fish fillets and chicken patties, which no longer had to emerge as a steaming tragedy, but could now offer a satisfying crunch. The Susceptor hadn't just created a better microwave meal, it had redrawn the map of the frozen food aisle, creating an entire continent of convenience where before there had only been desolate compromise. The industrial avalanche of Susceptor-based products created a new and stable reality in the American freezer aisle. The success of the crisping sleeve had neutralized the microwave as a source of culinary failure. It now represented the undisputed territory of speed and convenience, a 2-minute solution for a single-serving meal. This very victory, however, presented a profound strategic challenge to the other side of the aisle, to the companies that had bet on the conventional oven and on selling a 20-minute premium experience. With microwave pizza no longer a soggy punchline, the simple quality advantage of an oven-baked product was no longer a sufficient marketing platform. The battle was no longer crispy versus soggy, it was now fast versus slow. This strategic crossroads was where the counterpart story, the lineage of the raw, rising crust pizza, re-emerged with decisive force. The engineers and marketers at Kraft, who were preparing to launch their own rising crust entry into this market, arrived at a brilliant and counterintuitive realization. Their competition was not the 2-minute Hot Pocket or the 90-second microwave pizza. Arguing against that kind of speed was a losing proposition. Those products served a different need state, a different customer at a different time of day. Their true competitor, the one they had to defeat in the mind of the consumer, delivered its product to the front door in about 45 minutes and cost 3 times as much. The competition was not the freezer aisle, it was the local delivery pizzeria. This was a fundamental reframing of the entire category. This insight found its ultimate expression in 1995 with the launch of DiGiorno Pizza, and a marketing slogan that would become one of the most effective in food industry history. It's not delivery, it's DiGiorno. The brilliance of this line was its direct and audacious comparison. The slogan didn't claim to be better than another frozen pizza. It implicitly claimed to be indistinguishable from a fresh-baked, restaurant-quality product that cost upwards of $20. It reframed the 20-minute bake time not as an inconvenience compared to the microwave, but as a massive time and cost savings compared to waiting for the delivery driver. The implications were profound. This single campaign elevated the entire premium frozen pizza category from a compromise into a value proposition. It established a new battleground in the American kitchen. The war was no longer about the physics of crisping a crust in a microwave. It was a war of economics and perception, fought over the definition of quality itself. By consciously framing its product against the pizzeria, Kraft and its competitors in the oven-baked segment created a clear and powerful schism in the freezer aisle. On one side stood the marvels of material science, the Susceptor-enabled snacks offering speed and convenience, and on the other, a new class of product that promised something once thought impossible, the quality of delivery, straight from your own oven. This strategic schism, born from the divergent responses to the microwave crisis, was not a temporary state. It hardened into a permanent division, creating the modern frozen pizza aisle as the direct, tangible result of a two-front war. These two fronts, though originating from the same problem, were fought with different weapons, for different territory, and on entirely different philosophical ground. One front was a war of physics, fought for absolute convenience. The other was a war of perception, fought for uncompromising quality. The first front, the battle for convenience, was defined by the legacy of the Susceptor. Here, the objective was speed, measured in seconds. The technology was a masterpiece of material science, a microscopic layer of vaporized aluminum on a disposable sleeve, a device born from the physics of stealth aircraft, now deployed to wage a 90-second war against sogginess. This was the territory of the quick snack, the after-school meal, the solo dinner. It was the world of the Hot Pocket, of the single-serving microwavable pizza, where the promise was not culinary excellence, but a hot, crispy and satisfying result before the consumer had time for second thoughts. The second front, the battle for quality, was defined by the triumph of the conventional oven. The objective here was not to beat the clock, but to beat the local pizzeria. The technology was one of biology and chemistry, cryo-resistant yeasts and dual-stage leavening systems designed to turn a frozen block into a fresh-baked product with an airy, rising crust. This was the territory of the family meal, the weekend dinner. It was the world of DiGiorno, a world that intentionally ignored the promise of speed in favour of a 20-minute bake time that was framed as a direct, cost-effective challenge to restaurant delivery. The final and most profound irony of this half-century-long conflict is how it is being waged today. The two opposing armies, having carved up the market into their respective territories of convenience and quality, are now owned by the same generals. In 2010, the food conglomerate Nestlé, which had previously acquired Chef America and its category-defining Hot Pocket in 2002, completed the purchase of Kraft's frozen pizza division. This single transaction placed DiGiorno, the champion of the quality front, and Hot Pockets, the icon of the convenience front, under the same corporate banner. The two-front war for the freezer aisle had become a civil war, a strategic battle that the food giants now fight against themselves.